In this lecture, we are going to study the solution of partial differential equation using the Fourier transform, that is application of Fourier transform using PDE. So, first thing what we have to study is that what are the condition under which I should use Fourier transform, or when should I use Fourier cosine transform, or when should I use Fourier sine transform, and what is the required conditions, because unless the conditions are matching, I cannot use any one of these transformations. Like for Laplace transform, I gave the conditions for which I need to know certain values, then only I can find out the solution, or I can use the Laplace transform. Similarly, there are certain criteria. If those criteria or conditions are fulfilled, then only I can use either Fourier transform or Fourier cosine or Fourier sine transform. So, first we will study that part, that what are the conditions required to solve these problems. So, in application of this solution Fourier transform in solving PDE, first I am taking the criteria for choosing general Fourier transform. Obviously, if you remember, a Fourier transform has been defined from minus infinity to infinity. From the definition, we know that the Fourier transform with respect to x means x should vary from minus infinity to infinity. Therefore, the first condition should be one of the independent variables, because usually there will be two independent variables. At least one of the independent variable should have the range from minus infinity to infinity. If one independent variable has the range from minus infinity to infinity, then we can apply Fourier transform with respect to that variable only. If the variable range is something different, then please note that we cannot use the Fourier transform. And the second point is both the v and del v del x, or you can say u and del u del x, must vanish as x approaches plus infinity or minus infinity. I will tell you why this is required, but please note that both u and del u del x must vanish as x approaches the plus minus infinity. So, two conditions are given. One is one of the number one, you have to check I have two independent variables in general for the second order PDE. Out of them, at least one independent variable must be there whose range or which varies from minus infinity to plus infinity. Then only I can apply Fourier transform with respect to that variable. Point number two, both the function v and del v del x must vanish as x approaches plus infinity or minus infinity. Please note this one. If these two conditions are not satisfied, I cannot use the Fourier transform. Now, you will ask that why the second condition is needed. Let us see why second condition is required over here. Similarly, just I will come to that. Before that, let me just go through this one. Before that, let me go through the criteria for sine and cosine, then from there itself it also will be clear. So, applying sine transform, if I want to use sine transform to remove del 2 v del x square, then what will happen? For this one, you have this one 0 to infinity sin alpha x into del 2 v del x square dx. I am not taking root over 2 by pi or 1 by root 2 pi, that thing. Usually, if I omit that thing, then the Fourier sine transform of the function del 2 v del x square is this integral. So, if you evaluate this by parts, this will be del v del x into sine of alpha x, limit will be from 0 to infinity minus alpha into 0 to infinity cos of alpha x into del v del x dx. So, this will be equals to minus alpha into 0 to infinity cos of alpha x into del v del x dx. I can write down this thing if and only if in the first part for x equals 0, this part vanishes, that is fine. But for x equals infinity, what happens? For that one, I have to tell that this will be true only when del v del x approaches 0 as x approaches infinity. Then only this entire term will be vanishing, this term will be vanishing. For lower limit, since sine is there, it is vanishing. But for infinity, this term we cannot predict anything, and this term will vanish only if del b del x approaches 0 as x approaches infinity. So, this condition is required for us, otherwise we cannot find the solution. Similarly, whenever I am evaluating next, I will obtain minus alpha into v cos alpha x 0 to infinity minus alpha square into 0 to infinity. This will become v into sin alpha x into dx, and this is equals to at 0, lower limit at 0, this value is 0, this value is 0. So, this I can write down, this will be plus for the lower limit, alpha into value of v at x equals 0 minus alpha square into, this is nothing but the Laplace transform of Fourier sine transform of v, 0 to infinity v sin alpha x dx. So, this will be alpha square into v bar s. Here again I made one assumption. The assumption is if v approaches 0 as x approaches infinity, because whenever for x equals 0, I am telling it the value of v is needed at x equals 0, but at x equals infinity I cannot tell what is this. Therefore, the value should be equals to the 0. If it vanishes, then I have to assume this. Therefore, whenever I want to take the sine transform on a particular variable with respect to x, if I am taking these two values, I have to know, that is b approaches 0 as x approaches infinity and del v del x approaches 0 as x approaches infinity. Unless these two conditions are supplied to me, I cannot talk about anything, that I cannot evaluate this particular integral and I cannot get it. Therefore, whenever I take sine transform of a function, this is 0 to infinity sin alpha x del 2 v del x square dx equals alpha into v at x equals 0 minus alpha square v bar s, provided I know that b approaches 0 and del b approaches 0 as x approaches infinity. So, if you just see it, for removing del 2 v del x square, I am basically taking 0 to infinity sin alpha x into del 2 v del x square dx. Using integration by parts, I can write down this integral which I mentioned. Now, the first part will vanish only if I know del b del x approaches 0 as x approaches infinity, because for x equals 0 the term vanishes. So, here the first condition comes that del v del x approaches 0 as x approaches infinity. Again, if I integrate it, I will obtain this. For the first limiting value for at alpha equals 0, I am obtaining alpha into v at x equals 0, and for the second term for x equals infinity, I am assuming that b approaches 0 as x approaches infinity, and 0 to infinity v sin alpha x dx is nothing but the Fourier sine transform of v, which we are denoting as v bar s. Similarly, if I have to remove the cosine transform in case of del 2 v del x square, what condition is necessary? So, please note one thing here, 0 to infinity, whenever I am taking Fourier sine transform of del 2 v del x square, this is equals alpha v at x equals 0 minus alpha square v s bar, where v s bar is nothing but the Fourier sine transform of x, sine transform of v. Now, to remove this one del 2 v del x square, let us start similarly from this position, 0 to infinity cos of alpha x into del 2 v del x square dx. This is again on the same way, using the integration by parts, I can write down this is del v del x into cos of alpha x 0 to infinity plus alpha into 0 to infinity sine of alpha x into del v del x into dx. In the first part, you see cos 0 is 1. So, this value will be in the minus part del v del x at x equals 0. Here again you are assuming one thing, whenever x approaches infinity, del v del x will approach 0. Please note this one. Otherwise, for x approaches infinity, I cannot evaluate this value. So, I am assuming del v del x approaches 0 as x approaches infinity. So, that term will be 0 for x equals infinity plus alpha into 0 to infinity sine of alpha x into del v del x dx. And here you are assuming that if your del v del x approaches 0 as x approaches infinity. So, this is has to be known to us, otherwise I cannot use Fourier cosine transform. So, this equals minus del v del x at x equals 0, and again if I use the by parts, then alpha into v sine of alpha x from 0 to infinity minus alpha square into 0 to infinity v of v into cos of alpha x into dx. And note this integral 0 to infinity v of cos alpha x dx, this is nothing but Fourier cosine transform of v. Now, here again at whenever I try to evaluate this integral, this equals minus del v del x at x equals 0. This is known to me. Whenever you are putting the lower limit, since sine is there, that will be vanishing. But when I am putting the upper limit, then again I have to assume that v approaches 0 as x approaches infinity, then only this term will vanish. Otherwise, I do not find the value of this at x equals infinity. So, I am making the assumption that v approaches 0 whenever x approaches infinity, and this term I can write down minus alpha square into v bar c, where I am writing if v approaches 0 as x approaches infinity. Therefore, whenever I want to use the whenever I want to use the Fourier cosine transform, I have to talk about, I have to know that v approaches 0 and del v del x approaches 0 as x approaches infinity. If this condition is not there, then I cannot evaluate this thing. So, whenever you take the Fourier cosine transform of del 2 v del x square, this will be reduced to minus del v del x at x equals 0 minus alpha square into v bar c. So, you see this thing here, I am using here now 0 to infinity cos of alpha x into del 2 v del x square dx. This I am writing by parts as this. This equals minus del v del x at x equals 0 plus alpha into this integral. Here my assumption is del v del x approaches 0 as x approaches infinity. Now, again use by parts for the evaluation of second integral. So, you will obtain this. For evaluation of this, for the x equals 0, this part will vanish, sin alpha x is there, and for x equals infinity, again I am assuming that b approaches 0 as x approaches infinity. So, therefore, if I assume this, then this term will vanish and the integral 0 to infinity v cos of alpha x dx is nothing but the Fourier cosine transform of v, which we are denoting as v bar c. So, therefore, 0 to infinity or Fourier cosine transform of del to v del x square dx is equals to minus del v del x at x equals 0 minus alpha square into v c bar. So, now what is the criteria for choosing Fourier cosine transform? At least one of the independent variables should have the range from 0 to infinity and apply Fourier sine transform with respect to that variable only. So, please note that for Fourier sine and cosine, the variable range of the variable is from 0 to infinity. So, therefore, at least one of the independent variable should have range from 0 to infinity, and we are applying Fourier sine transform with respect to that variable only. Number 2, the value of the unknown function v x t must be known at the lower limit, that is at 0, and of the variable which has the range. And number 3, the behavior of v x t and del v del x at x equals infinity should be known. Please note that behavior means what can be the possible values, what kind of values it can have. It may be constant or it may approaches 0, whatever it may be. If it is not applied, then we assume that v and del v del x approaches 0 as x approaches infinity. This condition 2 and 3 we have shown it over there, the reason for using this thing. So, please note that the criteria for choosing Fourier sine transform is number 1, at least one of the independent variables should have the range from 0 to infinity, and you apply Fourier sine transform with respect to that variable only. The value of the unknown function v x t must be known at the lower limit of the variable, that is at x equals 0, where the range is from 0 to infinity, and the behavior of v x t and del v del x at x equals infinity should be known, or in other sense what should be the possible values. For physical problems in general, v and del v del x approaches 0 whenever x approaches infinity. So, this is the criteria for Fourier sine transform. Similarly, the criteria for choosing Fourier sine transform is at least one of the independent variable should have the range from 0 to infinity, like Fourier cosine transform, and apply not Fourier sine transform, but Fourier cosine transform with that with respect to that variable only. Number 2 is here the condition is the value of the function del v del x must be known. You see the difference. For Fourier sine transform, the value of the unknown function or value of the function v must be known at the lower limit, whereas for Fourier cosine transform, the value of the unknown function del v del x must be known at the lower limit, and this we have told why this is required. And the number 3 is the behavior of v x t and del v del x at x equals infinity should be known, and if not applied, then basically v and del v del x approaches 0 as x approaches infinity, what we have shown over there. So, these are the conditions or criteria for choosing the appropriate transform. Whenever a problem will be given to me, I have to choose basically whether I should use apply Laplace transform or Fourier transform or Fourier cosine transform or Fourier sine transform. So, depending upon the criteria provided to me, depending upon the initial conditions provided to me, depending upon the range of the variable, I have to decide or I have to choose the appropriate function. Let us quickly see one problem. I want to solve this problem del to u del t equals k del to u del x square with u x 0 equals 0 when x greater than 0. del u del x equals minus mu, which is constant when x equals 0, and u del x approaches 0 as x approaches infinity. So, for the function basically x is del u del t is del u del t equals k del 2u del x square. The range is given as x lies between 0 to infinity. If you note this particular problem, you will find that here they have not talked anything about t. What is the range of t? That is actually not known always. In one case only we are given that t greater than 0. So, since the value is given u x 0 equals 0 and del u del x value is provided, therefore, we apply the Fourier cosine transform on this to find the solution. So, you take Fourier cosine transform with respect to x on this. So, that root over 2 by pi will come. Your equation is, I am directly writing from definition, 0 to infinity del u del t into cos of alpha x dx. This is equals k into root over 2 by pi 0 to infinity del 2 u del x square into cos of alpha x dx. This gives me what? What is this? I can bring this del t outside, that is I can make it d dt. Then what will be it? Root over 2 by pi 0 to infinity u into cos of alpha x dx, which is nothing but Fourier cosine transform of u, which I am denoting as u bar c. So, the left hand side is u bar c. This is equals to k into root over 2 by pi into, here if you use the by parts, del u del x into cos of alpha x 0 to infinity plus alpha into 0 to infinity del u del x into sine of alpha x dx, which is equals to k into root over 2 by pi into this value. One value is known, at x equals 0, your del u del x is equals to minus mu has been told. So, that at x equals 0 minus mu, so lower limit. So, therefore, minus mu will become plus mu, and other term del u del x approaches infinity, approaches 0 as x approaches infinity. In the condition it is provided. So, that limit will be vanishing. So, for this part, for this del u del x cos of alpha x 0 to infinity, you will get only this plus alpha into 0 to infinity del u del x sine of alpha x into del u del x dx. So, please note that del u del x, this is equals minus mu for x equals 0, and your del u del x approaches 0 as x approaches infinity. Using these two conditions, I am getting this thing. So, once I get this, so I can again write down, which implies d dt of u bar c, this is equals to k into root over 2 by pi mu plus, again the integral I am breaking. So, it will be u into sine alpha x 0 to infinity minus alpha square into 0 to infinity u cos of alpha x into dx, and this equals, I will get root over 2 by pi into k mu, and this is nothing but, again this integral is the Fourier cosine transform of u. So, that this becomes k alpha square u bar c. Please note that u approaches 0 as x approaches infinity. This is also given to us. By that way, the value of this limiting value becomes 0. So, I am getting d dt of u bar equals root over 2 by pi k mu minus k alpha square u bar c. So that the equation now I can write down d u bar c dt plus k alpha square u bar c. This is equals to root over 2 by pi into k mu. So, basically your PD is converted to the ODE only, first order ODE only, and I am finding the I have to find out the solution of this. The integrating factor for this is integral of k into alpha square dt. So, that this integrating factor will be k alpha square into t. So, that the solution of this ordinary differential equation you can write it as e power k alpha square t into u bar c. This is equal some constant of integration a plus root over 2 by pi k mu into integral of e power k alpha square t dt. And if I simplify it, I will obtain u bar c equals a e power minus k alpha square t plus root over 2 by pi into mu by alpha square. So, I am getting this from here. So, now what is there? So, basically I obtained u bar c. Now, I have to find out the value of the constant of integration a equals 0. I know this thing u equals 0 from the given conditions. If you see the given conditions, it is known to us that u equals 0 at t equals 0. So, that at t equals 0, I can write down at t equals 0 u bar c, that is the Fourier cosine transform of u also will be 0. Since at t equals 0, u is 0, so I can write down at t equals 0, Fourier cosine transform of u bar will be 0, and you substitute it in this given equation, this thing, that at t equals 0, u bar c equals to 0. So, once I put this, I can obtain a equals minus root over 2 by pi into mu by alpha square. So, once I obtained the value of the constant a, and if I substitute it here, I can obtain the value of this u bar c over here. So, what I will obtain is that u bar c, this is equals root over 2 by pi into mu by alpha square into 1 minus e power minus k alpha square into t. Now, take inverse Fourier cosine transform on it to obtain the value of u x t. So, u x t is equals to root over 2 by pi 0 to infinity from the definition u bar c into cos of alpha x into d alpha. And now, u bar c, you know this thing. So, if you put the u bar c, it will be twice mu by pi 0 to infinity, u bar c is cos of alpha x by alpha square into 1 minus e power minus k alpha square into t into d alpha. So, u x t I am obtaining this integral 2 mu by pi 0 to infinity cos of alpha x by alpha square into 1 minus e power minus k alpha square t into d alpha. If I evaluate this integral, I will obtain the value of u x t. So, please note that for finding the solution of an partial differential equation second order PDE using the Fourier cosine transform or Fourier sine or Fourier transform, we have 3 steps. First step is take the Fourier cosine transform with respect to t. Once I am taking the Fourier cosine transform, your given second order PDE will be converted to a first order ODE. Find the solution of the first order ODE using the normal techniques. Once you are finding the solution, you will get one integration constant. By given condition, find the value of the integration constant, and you can obtain the u bar in terms of the x and s and t alpha and t, and once I have obtained the u bar, then using inverse Fourier cosine transform you can write down u x t equals root over 2 by pi 0 to infinity u bar c into cos of alpha x into d alpha. So, this is the process. In the next lectures also we will proceed with this, and we will give you more examples on it, so that you can understand it in much better way.